our guest today, Suzanne Bintanja, I hope I pronounced correctly, who will tell us about a particularly interesting topic on thermal universality in symmetric product orbifolds. So please, Suzanne.
Thank you a lot for the invitation. It's been my first visit to China, and it's been really beautiful, really nice. So yeah, I'm very happy to be here. And yeah, today I will talk about this recent work that came out in February. And I worked on this topic together with Alex Bellin, who's in Milan, Hanna Castro in Cambridge, and Waltraud Knop, who is in Stony Brook. So here's the outline of the talk. I'll start by motivating the topic from the point of view of holographic CFTs. Then I'll quickly discuss symmetric product orbifolds and their universal properties. Then we'll get to the meat of the talk and talk about thermal correlators in this class of theories. And I'll finish by discussing gravitational implications and future directions. So at the start, I'll go maybe a bit quick, but please feel free to ask questions at any time. I'm happy to explain more if people are curious. So one of the main insights that we've had in the past few decades is that the true microscopic degrees of freedom of a theory of quantum gravity are located at the boundary of space-time. And the gravitational theory should be seen as an emergent description in the bulk of this boundary. And this idea is realized explicitly by the ADS-CFT correspondence for theories of quantum gravity that have a negative cosmological constant. And in this setup, the equations of motion and the variables should be seen as emergent effective properties of a subset of the true microscopic description in terms of the CFT on the asymptotic boundary. There's 2 slides of every slide. Anyway. But for this picture to work accurately, the boundary CFT has to be a very special CFT within the space of all possible CFTs. And we call such CFTs holographic CFTs. And many necessary conditions that you have to put on your CFT such that you have a local emergent spacetime in the bulk are known, but at this moment there's no set of conditions that is sufficient. So there's no list of conditions that you can check, and if all the conditions are met, we know for sure that there is a nice bulk description. And the main strategy that people have used so far to tackle this question is to start with some desired bulk property, and then use the ADS-CFT dictionary to translate that desired bulk property into some implied property on the CFT side. And in this way, come up with conditions that are necessary to have a nice bulk dual. And this strategy has had a lot of success, especially in contexts where the bulk observables that we are interested in are taken to be scattering processes in vacuum ADS. And the hallmark paper where this program was started was this one from 2009. And the idea is to consider CFTs with a large number of degrees of freedom encoded in the stress tensor 2-point function through the central charge, which is large. And in bulk parameters, that means that the Newton constant is small, measured in ADS units. And so a large number of degrees of freedom corresponds to a classical limit on the bulk side. And the idea is to match couplings from the bulk EFT to solutions to the CFT crossing equations, and in this way learn about bulk EFT from the CFT side. And in this way, one of the most impressive results was that the suppression of higher derivative corrections to general relativity was related to the absence of higher spin operators in the CFT, or the large gap condition. And these are the people that worked on that. But for thermal observables, the situation is a bit more interesting. And the reason is that once we raise the temperature to be above the Hawking-Page transition in the bulk, thermal observables are probing black hole physics. And unsurprisingly, this makes thermal observables more complicated than their zero temperature counterparts. And it makes the question very hard to grasp. However, if we consider CFTs in 2D, we can use modular invariance to find powerful conditions on these thermal observables. Now there's one. And the main result, or the result that really got things going in this program, was worked out by Hartman, Keller, and Stoika, or HKS, who showed that having the correct phase structure of 3D gravity, which I wrote here in CFT parameters, imposes a sparseness condition on the light spectrum in the C to infinity limit of the CFT. So if your CFT has a large C limit and its light spectrum satisfies this bound, then the CFT has the correct phase structure, has the same phase structure as GR in ADS3. And in particular, that means that for a CFT that satisfies the sparseness condition, the entropy matches the Bekenstein-Hawking entropy whenever the BTZ black hole dominates the canonical ensemble in the bulk gravitational theory, and it has a Hawking-Page transition at the self-dual temperature. And under mild growth conditions of the OPE coefficients, these results can also be generalized to thermal correlation functions. But in recent years, a new perspective has been proposed, inspired by algebraic QFT and operator algebras. And the main observation behind this new idea is that in holographic CFTs, the operator algebra associated to simple operators in thermal states above the Hawking-Page transition undergo a drastic change. At finite C, they are type 1 von Neumann algebras, whereas at strictly infinite C, they are type 3. And this jump in the type of the von Neumann algebra associated to these simple probe operators was proposed to be a smoking gun for the emergence of a bifurcate horizon and an emergent local spacetime. Yes. Above the Hawking-Page transition. Yeah, below the Hawking-Page transition, the type is always type 1. Yes. Moreover, last year there was another paper with the same goal in mind. And LHS Sto and Hong Liu proposed a probe for the depth of the emergent radial direction in the bulk, as seen by a simple probe operator or probe field, using algebra considerations. And this probe was related to the possible stringy nature of the emergent bulk theory. And both these algebraic quantities, the type and this causal depth parameter is what they called it, are determined by the spectral density of thermal two-point functions of the operators in the dual CFT, dual to the probe field at infinite central charge. And so by understanding these kinds of thermal properties, we can test how strong these new algebraic conditions are from the field theory point of view. And that will be our goal today. We will look at this particular class of CFTs, symmetric product orbifold CFTs, and compute their thermal correlation. Yeah.
Charge limit is basically the zero flat thing.
Yes.
So, what is the parameter that corrects for higher derivative connections?
Well, you can have higher spin gravity, for example, and those will have higher derivative couplings, I think.
If I look at the string theory, the parameters alpha prime and JS, and JS the string coupling will holding corrections.
Right.
Is
But you could have like R to the 4 terms, right? I don't know from the top of my head. Well, it's this gap. It's the size of the gap of higher spin operators. I don't know if that answers your question. All right. Okay. So with that, let's move on to symmetric product orbifolds, the theories that we are interested in, if there's no further questions. Okay, so symmetric product orbifolds, they form a class of 2D CFTs that have a well-defined large central charge limit. And the way that you can construct them is to take any compact 2D CFT, X, that we will call the C theory. And the C theory is usually chosen such that it is under good mathematical control. But what I mean with any here is really any. And everything I will say today will be true regardless of the choice of X, as long as it's unitary and compact. Okay, and then given this C theory X, we can define a new CFT called the symmetric product orbifold of X. It comes with the parameter n, and it's given by the n tensor product and tensor power of X. So you take n copies of your C theory. This introduces a global discrete symmetry by the SN group or the permutation group of rank n, which acts by permuting the different copies of your C theory. And we gauge that symmetry. And that gives us the symmetric orbifold CFT. And this new CFT has a central charge given by n times the seat central charge. And so by taking n to be very large, we can have a good large central charge limit. And a very nice thing about this construction is that any observable in the symmetric orbifold theory can be computed in terms of the seat CFT. And thus it gives rise to a class of large n CFTs under good mathematical control, at least if you choose your seat theory to be under good mathematical control. But let me reiterate that everything I'll say is true regardless of the seat theory today. And the fact that we have gauged the SN symmetry has two consequences. First of all, the spectrum contains twisted operators, which have non-trivial holonomy. If I insert an operator on the jth copy of my tensor product and rotate it around the origin, then I can end up in the G of jth copy of my tensor product, where G is some element of the permutation group. So I have these extra twisted sectors, and moreover, every operator has to be gauge invariant. So it has to be invariant under permutations of the symmetric. And this implies that operators only depend on the conjugacy classes. Okay, very good. And symmetric product orbifolds have many properties that are universal once we take the large n limits, once we take the limit of having many copies of our seed theory. Some of them support a holographic interpretation in terms of a local emergent space-time. First of all, they satisfy the HKS sparseness condition that we saw before, so they have the correct phase diagram. And secondly, their light spectrum obeys large N factorization. And that means that light operators behave as generalized free fields. And on the bulk theory, that implies, on the bulk side, that implies that gravity is weakly coupled.
Sorry, Susan, just one that's rather precision. Since you mentioned you are considering any X manifold, which you can symmetrically product, but the point is, can you really still apply a covering map approach to compute correlators in this case?
Sorry, what can I use?
The cover map, something that Matthias is using every time.
Oh, yes.
Because in
Just
many
from-
examples, for any manifold, it can be problematic to find the conformal.
Called any unitary compact CFT.
Yeah. That should be, so you are saying like in those classes, unitary.
Yes. Yes, sure. The cover map. Yeah, no, it's very complicated. Yeah, the cover map is independent of your choice of C theory.
No, yeah.
Yeah, but that's also true in like K4 or K3. It doesn't depend on the C theory.
Yeah, sure.
Yeah, no, it's a mathematically. Yeah. No, these maps are very complicated, but there's no conceptual issue. All the data, although P coefficients are fine. Yeah. It will be difficult. It will be mathematically difficult. Yeah. Well, we will see that for thermal correlators, we can do it.
Yeah.
For certain classes of operators. All right, we'll get there. Be patient. Okay, so there are some universal properties that are nice for gravitational interpretation, but there's also some that are not consistent with the local emergent spacetime. They contain infinite towers of higher spin currents, or at least one. Here's just an example of what such a higher spin current can look like. T is the stress tensor on the C of the C theory. Furthermore, the out-of-time order correlator was proposed as a signature for chaos. In the bulk theory, it describes a scattering process close to the black hole horizon, and because black holes are chaotic, this OTOC decays. But for symmetric product overfolds, you can compute it by computing this 4-point function, and it does not decay, regardless of whether the C theory is chaotic or not. As we take n large, the chaos gets washed away. Right. Yeah, we don't know. Like, I think there's a connection between these two things.
And also, what you mean by a black hole in higher spin theory is also great.
Right. Yeah, I agree. Yeah, I mean above the phase transition. And finally, I said before that symmetric orbifolds satisfy the HKS bound. They not only satisfy it, but they saturate the bound on rho. So the light spectrum, it grows exponentially with the scaling dimension. And this is reminiscent or characteristic for a string-like spectrum. So the dual theory has non-local degrees of freedom because this growth is too fast. And in a local GR type theory, we expect to find the square root of delta here instead. And the take-home message of this review, or I think how we should think about symmetric product overfolds, is that they form a large class of theories that we can take a large N limit that are under good mathematical control and mimic gravity in non-trivial ways. And so just because of that, they form a rich and interesting playground to test and study holography. However, they do not have a gravitational interpretation in terms of an emergent spacetime, possibly weakly coupled to matter following the laws of general relativity. And so we should really think about them as toy models and not like actual models for quantum gravity, local quantum gravity. And the way that you can think about them is as like a 2D analog of free gauge theories in the large N limit, where in that setup N is the rank of the gauge. Nevertheless, there are certain specific choices for the seed theory for which we do know that there's a connection to holographic CFTs. The most famous ones are nonlinear sigma models on Kähler 3 or T4 manifolds, which appear in string theory and were already mentioned in the original ADS CFT paper and have been studied in many, many more papers. And in recent years, there's also been studied by me and Luis and many others. We studied N equals 2 minimal models as seed theory, and we found evidence for the fact that they might have something to do with holographic CFTs. And the reason why these theories have something to do with gravity is that they contain exactly marginal deformations, which define for you a conformal manifold. And turning on these marginal deformations can be thought of as turning on the gauge coupling. And by doing that, you break the orbifold structure, and the idea is that you drive the theory to a holographic form. But the theories have to be the seed theory has to be chosen very specifically and generically.
This seed theory is like is whether this marginal deformation cannot be found or is sorry, is this marginal deformation is not there or it's hard to find for generic seeds.
So the exactly marginal deformation has to be a little bit special. It has to be in the twisted sector as well. And it has to be exactly marginal. So that tells you you need supersymmetry. And the fact that it has to be in the twisted sector puts a bound on the central charge of the seed theory. It has to be less or equal than 6. So that already constrains you a lot.
Because in all those examples, the requirement discussion is for all of those everything to work out.
But well, imagine that I take in these N equals 2,2, there's instances that have multiple exactly marginal deformations of this form. Say I take one, I deform a little bit, my theory is not integral anymore, but it still has the other marginal deformation.
Yeah.
I think is not known. I think all the examples that we have are related to integral.
To start with, for general CFT and the large limit, then the theory does not make much sense. So, really, if you want to put holographic description, then you have to work at non-zero
Yes.
large limit at non-zero coupling, and then set the coupling to 0. So there's a specific order of limits. Maybe that's also what's happening here. That what you asked.
I'm saying those statements would that using like so that's really important. In some sequences of
Right.
sequences of double
Yeah.
that you can acquire.
All right. Very good. So with that, let's get to the meat of the talk and study thermal correlators in symmetric product orbifolds. And it will be useful to first look at the thermal partition function, after which we will study how to add operator insertions. As you all know, the partition function is given by a trace over the Hilbert space, where Q is e to the 2 pi I tau, and tau is the modular parameter of the torus. And so to compute this trace in a symmetric orbifold, we have to understand carefully how the twisted sectors contribute. And there's basically two formulas for the thermal partition function of a symmetric product orbifold that I'm aware of. One is in terms of a grand canonical partition function, where you make n also a variable. But for us today, this other formalism introduced by Bintanja in the late 90s will be more useful. And this formula, it tells us what to do with the seed partition function in order to find the partition function of the symmetric orbifold at any value of n. All right, and let me explain how to get this formula, or how to understand this formula. Like I said before, we have to understand how the twisted sectors contribute, and this can be understood through studying cover surfaces of the torus, like you said before. And for cover surfaces of the torus, are characterized by group homomorphisms of the fundamental group. No, not the fundamental group. Yes, the fundamental group of the torus, which is the direct product of the integers into the gauge group Sn. And such homomorphisms are labeled by commuting elements of Sn, G and H. And so this is where the sum G over G and H comes from. This is a sum over all possible coverings of the torus. Generically, each of these cover surfaces, so each of the elements of the sum, has multiple connected components, each of which is again a torus due to the Riemann-Hurwitz formula. So a cover surface will be some direct product of tori. And such connected components are labeled by orbits in this set, which is the set of orbits coming from the abelian group generated by these commuting elements G and H, acting naturally on the number of copies, so 1 through n. And such orbits are in one-to-one correspondence to 3 integers, lambda, nu, and kappa, which there's a way to compute them for each orbit, but for now, what's important is that there's 3 integers which tell you everything you need to know about the orbit. And so the partition function associated to that connected component, so this is just one single cover torus, is just given by the seed partition function evaluated on that torus. And this cover torus has a slightly different modular parameter, namely this one. So it's related to the modular parameter that we want to evaluate our symmetric product orbifold partition function on. But it's multiplied and divided by, in this way, by the integers that specify the orbit. So that's maybe a bit much. Let's look at an example. Here above, I've drawn 2 tori. They have 2 cycles, as we all know. And here I drew the direct product of the first 2 copies, but you can imagine that there should be n of these tori. Now let's look at the contribution to the sum coming from picking G, the permutation that swaps the first and second copy, and H to be trivial. That means if you study the orbits, that there's a single non-trivial orbit, which comes with modular parameter tau over 2. And the cover surface, what it will look like is that copies 1 and 2 get cut open and glued together in this way. So this side of the torus you can think of as what remains behind, of course, torus number 1 of torus associated to copy 1, and the right-hand side coming from torus number 2. And all the other copies just go along for the right. So this kind of gives us a nice interpretation as to what these cover or these elements G and H are doing. Both G and H, they are just telling us what is the non-trivial holonomy as I go along the different cycles. G is telling us what happens if I go once around this cycle, and H is telling us what happens when I go around this cycle. Okay, very good. And the intuition that we can use is that different choices for G give rise to the different twisted sectors, whereas different choices for H will take care of projecting out charged operators. So H takes care of the symmetrization over Sn. And to understand the contribution of more general twisted sectors, or let's consider H equals 1. We don't care right now about symmetrization, but let's take G now to not be a single non-trivial cycle of length 2, but we'll have a cycle of length L. We'll be interested in taking L to be large and close to N. Again, there's one non-trivial orbit. It now has modular parameter tau over L. And so this term in the sum, it contributes this combination of C partition functions. And when we take L to be large and think about the dominant contribution, we can write it in terms of the density of states. There's n minus L factors of the usual or trivial copies of the seed density of states. And then from this length L cycle, we get a factor of rho evaluated at L times the scaling dimension. And now when we take L to be very large, we can use the Cardy formula for this factor. And when we take L to be large, this first factor should not be important for the dominant contributions because it comes with this power n over L. So with those things in mind, you can find the scaling, and it scales in this way. And so let's see at what L's and what deltas dominate this square root behavior. You can do a simple saddle point approximation. And what you find is that this expression is maximized by cycles with this length, or equivalently is maximized by values of delta that are related to L in this way. And so when you work out what that means, you find precisely exponential scaling that was that I advertised just before. Now remember that we only looked at one choice for G and H. In principle, you have to sum over all of them, or not in principle, you really have to sum over all of them. But what was shown in the paper by Christoph Keller is that including the other terms in the sum does not increase this exponential Hagedorn behavior. And so we found universal Hagedorn growth in the symmetric product orbifold, regardless of the seed theory. And we can understand this Hagedorn growth as coming from the long twist cycles. And this is showing a very powerful technique of showing these universal properties in the large N limit. We take these long twisted cycles, and when you carefully analyze what that means for the quantities in the seed theory, it means that you can often approximate them by the universal high temperature results, which we saw here in the fact that we could use Cardy's formula for this factor of rho evaluated at L times delta. And so that's also what we'll use for the thermal correlators.
become negative also, make it extremely large.
L can never increase.
So you have the different formula,
Hmm?
and then you, this was just symbolic growth of this cycles with this length, and just having like one long cycle and a bunch of
Yes.
right? And then you have this formula, and then you find what maximizes it.
Yes.
The cycles of this length, but then you get Hagelin
Yes.
growth. But where is this formula about it? The first one I thought was
This one is at large L compared to N, like, or not compared to N. N is always larger than L.
first state above the black hole.
No, it's below.
Below.
You can never. In this way, I don't think you can go above.
So you're saying the density of these things below the black hole pressure. Looks like that.
Yes,
And
exactly.
then I see what the maximizes. But also above the black hole pressure, because the things that contribute the most are also the known. At single twist, the maximum distance.
Yeah. Yes, and we'll see that for the thermal correlators. Yeah, I don't have an intuitive understanding
But so
about how that works.
I thought about the
Hmm?
phase transition, it was that all states in principle contribute.
Yeah.
But the maximally twisted ones start contributing earlier.
Right. Yeah, but maybe one interpretation is that here we are starting to see that onset.
That's-
Because the Hagedorn growth, it's true for scaling dimensions that are parametrically larger than 1, but still below the black hole threshold. All right, so thermal correlators. To find thermal correlation functions, we now all we have to do is to add operator insertions to our trace. So this is the definition. And here we haven't added the usual normalization by the partition function. You can do it. It's just less cluttery notation without it. And we will consider 1 and 2 point functions of untwisted single trace operators. And for simplicity, we'll consider scalars, but you can do also operators with spin. And we will suppress the anti-holomorphic dependence where possible. Now, generalizing to higher point functions is straightforward. And also generalizing to multi-trace operators that are untwisted is straightforward. However, generalizing to twisted operators is very subtle and confusing. We have a heuristic argument as to what should happen, but we cannot write equations. But you can ask me after if you're interested to hear the story there. But so the operators that we'll consider, we can write them in this way, just as a sum over seed insertions inserted in all the different copies of my tensor products. And so we have to think about what does it mean to add a seed insertion on my torus. And so now I have again n factors of my torus, But now on one of them, I add an insertion. And I sum over all different choices for where I add this operator. And so intuitively, it's clear what should happen. When I again look at my example where G just swaps copy 1 and 2, if my insertion is on copy 1, I should just add it in my cover torus on copy 1. If my seed insertion is instead on copy 2, I should insert it in the appropriate place on this side of the cover torus. And so when going to the cover surface, if I have an insertion, I should just add it in the usual place and then add appropriate images along the increased cycles of the cover torus. And so to write that in equations is a little bit cumbersome, and to help us, we define a function g that's given an orbit, provides the cover surface with the relevant operator insertions and includes their appropriate periodic imaging. So I have my orbit psi, modular parameter tau, and some number of seed insertions. Here you can define this function for any n that you like. And on the right-hand side, we have a sum over torus correlation functions of the seed theory, evaluated on the torus with modified modular parameter tau psi. And the location of the seed insertion has to be changed because we used this conformal transformation of tau. And under that conformal transformation, z transforms in this way. So we have to divide by lambda. And the sums over J and L, they are just the sums over all these different periodic images appropriately added. Okay. And so with that, we can now write the torus 1 and 2 point functions. The 1 point function is the simplest. I have my sum over cover tori, and now for each orbit, I have to sum over my operator insertions in the copies associated to that orbit. So I have my G showing up here. But for all the other orbits, nothing should happen, and I just multiply with the partition function expression that we've seen before. And the 2 point function is basically the same, except that now there's two different choices. I can choose, or there are instances where my seed insertion is inserted on copies that are in the same orbit. Then I get this, this term. But there's also instances where my seed insertion is inserted in different orbits. And then you get sort of what kind of looks like a disconnected term. And I multiply again over all the other orbits. All right. Okay, is that clear-ish? If so, let's do an example, and let's again look at the h equals 1 term and g to have one long cycle. First, to get a feel of things, and second, this one was the important one to find the universal behavior for the partition function. And so in the same way, it will be important for universality in the thermal correlators. All right, so first let's look at the 1 point function. There's n minus 1 or n minus L instances where my seed insertion is on one of the trivial cycles of G. In those cases, I just have my seed insertion on the usual or on the torus with modular parameter tau. And then the length L cycle, it just shows up as a partition function. And then there's L other contributions where my seed insertion is inserted in the non-trivial cycle. And this non-trivial cycle is evaluated on a torus with modular parameter tau over L. And these two terms, they both go to 0 as I take L to n and n to be large. The first term is easy to see just because of the prefactor. This thing becomes small and we have suppression by square root n. For the second term, we have to work a little bit harder. And we have to realize that when I take tau to be equal to I beta, which is the usual relation to the temperature, and I take L to be large, then this is precisely the high temperature limit of 1-point functions. And in any CFT, when I take beta to 0, my 1-point functions vanish, and they're exponentially suppressed in L, which is large. Okay, so next let's look at the 2-point function. There's a bunch of different terms, 2 of which I wrote here. The first term is where both my seed insertions are inserted on the non-trivial cycle L. And the second term here on the bottom is where I inserted the seed insertions in one of the trivial cycles of G. Now there's 2 other terms where my seed insertions are inserted on different orbits in different cycles, but those are small in the large n limit because of this reason, or for this reason. They appear in combinations that look like this. Excuse me. Okay, very good. So let's analyze this expression that I just repeated from the last slide, and realize that we can use the same high temperature limit when L gets close to n to evaluate this term. And we can use the universal high temperature limit of any thermal 2-point function in CFTs, because as before, beta is suppressed by this value L that we take to be large. This is the universal expression, and we can just insert that into this expression. And what we find is this: there's this factor of L, which comes from the conformal transformation of going to the cover torus, and then this is what you get when you fill in the high temperature limit for the thermal 2-point function. Now there's also the other term, but this one is suppressed when L is large. Okay, so we found already something that looks pretty simple. And when we take both n and L to be large, we can simplify even further by replacing the double sum with a single sum over all the integers. And we get this very nice looking expression. This one?
Yeah.
It comes from the fact that I insert beta over L.
Oh.
And so the L's here cancel, and also the L's in the sinh cancel. So all the L dependence cancels out, which is nice. Okay, but now we have to ask, is this contribution leading? We only looked at this one particular cover surface. And if it is, what is its regime of validity? And here I'm going to cheat a little bit and argue that we can just use the result for the thermal partition function. So for the partition function, we could argue that this H equals 1 and G equals L gives the leading order behavior, and the leading order behavior is valid all the way to the phase transition at 2 beta, which is what HKS is telling us. And we expect the same to be true for thermal correlation functions of light operators. Because we only add insertions that are light, they are not expected to affect any large n dominance, they're just changing the order 1 dynamics. And the regime of validity should thus be determined by the same considerations as one would use just for the thermal partition function. And a similar effect is true. A similar effect is true when you look at path integrals in QFT. The dominance of a saddle is not expected to depend sensitively on any light probe of that saddle, at least when you're sufficiently far away from any phase transition. And so our very simple expression should be true for all high temperatures, all the way to the phase transition at beta equals 2 pi. And so let's recap what we have found and try to understand what does this mean for gravity. To aid the gravitational interpretation, we write our results in terms of an angular coordinate and Euclidean time. And I've added back in the anti-holomorphic dependence. That's here. And recall that we looked at scalars, so the h's are the same. But this formula would be equally valid if h bar was different. But because we look at scalars, I can simplify the expression and write it in terms of a cosh and a cosine. And like we just argued, this expression should be valid above the Hawking phase transition. And so this is the universal answer for the thermal 2-point function of light untwisted single trace operators in any symmetric product overfield. And the low temperature expression can be obtained simply by doing a modular transformation that relates beta to itself in this way, and it interchanges the two cycles, phi and Euclidean time.
Try to compute the same coordinate of holographic in thermal radius and
Yes.
then do modular transformation in the high temperature.
Exactly. Yes, and that's what I did here. I wrote down the full expression for any temperature. We know what is the answer at large n for the thermal 2-point function. And well, if we could click, then this would still be a surprise, but you can already see what is happening. This is precisely, in case you didn't recognize it, this is precisely the 2-point function of a scalar field inserted at the boundary of the BTZ geometry or thermal ADS. And so thermal 2-point functions in symmetric product orbifolds are identical to those computed in 3D gravity. And this fact was very surprising, or is surprising for a number of reasons. First of all, it is true for any seed theory. We never refer to any property of X, independent of whether this choice of seed theory has anything to do with gravity, and regardless of whether there is this gauge coupling that we can turn on in order to flow to a holographic point. But I want to argue that even for those very special seed theories, this result is pretty surprising, because thermal correlation functions are not expected to be protected along any conformal manifold, and that can be seen by their dependence on the entire spectrum of the CFT, due to the trace over the entire Hilbert space. So even there, I would argue that this result is kind of surprising. And in the language of operator algebras, our results can be phrased as follows. The operator algebra associated to a single trace operator is identical to the operator algebra in a strongly coupled holographic CFT at infinite n. And so any holographic condition that depends or that comes from operator algebra considerations at infinite n cannot be sufficient to distinguish between a holographic CFT and a symmetric product orbifold, which is not holographic. And so that's what we learned, besides this nice result. That's the implication for holographic CFTs of our result. So let me summarize. I've been talking for a long time. Symmetric product orbifolds have many universal properties. Many of them support a gravitational interpretation in terms of semi-classical Einstein gravity, but there are also some that contradict it. In particular, and surprisingly, we've seen that at large n, their thermal correlation functions are identical to those computed in gravity. And thus, any condition or a condition on large n thermal correlation functions cannot be stringent enough to ensure a local emergent spacetime. There's many interesting and open questions that this result opens. First of all, is there an underlying explanation why our thermal correlation functions should match those of 3D gravity? Because it's quite remarkable. We've matched the full functional dependence of a 3-parameter function, and at least a priori, there's no first principle reason for that. Then one could ask what happens beyond the leading large n limit. There's 2 ways that I think would be interesting. One could try to just understand what are the other cycles, go back to our computation and see what is the next to leading order correction. But one could also try to probe the extremal limit. Here we didn't consider any angular velocity, but what one could try to take the extremal limit where you have a left and right moving temperature that scale very differently with n. And in this limit, it has been argued that higher spin currents are important. And we know that symmetric orbifolds have them, like gravity does not. So here you should start to see something. And that would be really interesting to work out. Then to what extent are symmetric product orbifolds chaotic? The OTOC says no, but having the thermal 2-point functions of BTZ black holes, it kind of begs for maybe some intermediate understanding of notion of chaos. And there's 2 hints that, or 2 ways in which you can imagine tackling this question. A couple years ago, there was this very interesting paper that gave a matrix model interpretation for cover maps of correlation functions at 0 temperature, but of operators with long twist cycles. And then also recently, there's been many interesting papers pertaining BPS chaos. And one could study this in symmetric orbifolds. And then finally, the big remaining or a big open question is, how should we think gravitationally about these symmetric product orbifolds? Should we think of some stringy geometry, or it's an open question. So yeah, that's all I have to say. Thanks a lot for listening.
Okay, there have been a number of questions, but let me see if there are more.
Maybe it's useful to try to distinguish between the analog of the Hooft coupling and the central charge, because then one can kind of, so the large central charge limit is truly a
Yes.
cyclic limit,
Right.
and the Hooft coupling being very large is the gravity limit.
Right.
So
Yeah.
there probably one could try to disentangle what is
Yes.
happening.
This is complicated
Yeah.
because you're starting to probe strongly coupled CFTs.
Okay.
We have some results in perturbation theory, like with Luis. We looked at what happens to these higher spin currents once you try to turn on this coupling. But I think for thermal correlation functions, like that's very far away. It's very.
And this
gets very-
matrix model interpretation for cover maps, does it come from this matrix model interpretation of topological string correlators? So like they would be.
Yeah, I'm not very familiar with topological
see.
strings, so I couldn't comment.
More along the lines of quantum volumes, or
So basically you think of this is an old paper by Ramgulan and Demelukok. Yeah, that construction where you think of topological string correlators as being
Yeah.
mapped from the world sheet to some embedding space, and that you can also realize as a matrix.
No, of course, yeah, because I think this is pretty universal from what I know.
Yeah, I can tell you the paper is that does this is by Bob Knighton, Gabardiel,
That's what I referred to.
Rangamani,
What I want
and
to
there's
just make a comment is that on this matrix model map, you can the cover map you can develop, I think, for any construction. This is how you can get the topological string correlate as well. But the actual problem is to find it.
So just you previously said that this stage of the product of where I have this particular person as a chaos. But here somehow you confident that you can actually see the correlate of the like the sum operation that's corresponding to the EP's exact whole, and you expect that this is chaos. So
no, I think there's it's quantum chaos is not yet fully fleshed out. We don't quite know, but there's this idea of ergodic hierarchy, where having a decaying OTOC is a very stringent, or like there's this hierarchy between different notions of chaos and mixing. And for example, having a type 3 von Neumann algebra was related to chaos in this setup. And symmetric orbifolds have that because, well, we showed it because their thermal 2-point functions are identical in the large n limit. But so let me maybe rephrase. When you think from this operator algebra point of view, you can this gives information about the chaotic nature of your theories. And symmetric orbifolds satisfy at least some of the conditions coming from that language. But they do not have the decaying OTOC. So they have some sort of notion of chaos, but not enough, not the same notion of chaos as what like gravity has. I don't know if that makes sense, but
so people cannot do similar like JT chaotic dynamic studies on here, right?
not at the free point.
So it looks like this BPS or chaotic dynamics of something intermediate, right?
Yes.
You cannot just introduce some
No.
matrix random ensembles.
No. Yeah, but then like this cover map is very intriguing to me. I don't know if like how we should think about it physically. I think there could be something interesting, but I don't really know how to interpret this fact at this point in time, but will be very interesting to understand.
Maybe very quickly. I'm just wondering, but can you at the algebraic level, when you pass to the large C to infinity, strictly speaking, and I mean to acquire this phenomenon algebra third type, does it provide the extra algebraic structure for the correlative computations?
I'm not sure.
So this is literally, you can see just that there is a transition that you can
formally
take.
Yeah.
You see.
Well, it's a bit unclear what happens if you're at or I think there's been discussions about what happens if you introduce 1/n corrections. Like something interesting happens to the operator algebras. I don't know the details of that story.
Not only if this algebraic third type structure captures.
Right.
Because I know people have similar in the gauge theories have this capturing in the large n.
Right. Yeah.
Okay. If there are no further questions, let's thank Susan.
To run for the bus.